Hello friends, welcome to follow up. Let's have a look at today's daily challenge problem. Problem 1266, minimum time visiting all points. So this is a very easy problem, but our point is to demonstrate how to do problem reduction or thinking in an abstraction fashion. So abstraction is actually very common in mathematics or in computer science, right? So here we have a 2D plane and there are endpoints with integer coordinates. So this is actually a very important assumption, right? So we want to find the minimum time in seconds to visit all points in the order given by points. So the rules are the following. We can move either vertically or horizontally or diagonally. So the last 2 points is that we have to visit the points in the same order as they appear in the array. And also we are allowed to pass through points that appear later in the order, but these do not count as visits. So actually these 2 bullet points make the problem much easier, right? So here we have 2 examples. So let's start from example 2. So in example 2, the points have same y coordinates. So the minimum visiting time will be the difference in their x coordinates. That will be 3 minus -2. We take absolute value, right? So this is 5. But 3 is, if you use the larger one minus smaller one, so it will equal to the absolute value. This is 5. So this is the case for the 2 points have same y coordinates. So this is the same if they have the same x coordinate. We just need to compute the absolute difference between y coordinates, right? So example 2 basically covers the generic case. But this problem essentially reduced to compute the visit time between 2 points. Because of the 2 bullet points here, we just need to accumulate the result, right? For each pair, this pair and this pair, right? So in generic case will be, let's see, reduces to compute visit time for any given 2 points, right? So this actually is the problem. So here, if you look at 1, 1 and 3, 4, so we are going to see, so this need 3 steps. So we can do this 2 step diagonally and 1 step vertically, right? So for this pair, so if you look at their x coordinate difference will be 4 and y coordinate difference will also be 4 in absolute value. So this needs 4 steps. So here is the specific way. 3 plus 4 is 7. But in this problem, in order to get the time, we don't need to know the specific ways of traveling. So here, let's see how to think of this problem. First, so we reduce this problem to compute distance given 2 points, say P0 and P1, right? So here, P0 and P1 will be something like this, x, y, right? So see x or AB, let's see, something like this, right? So we want to return the visit time. But in general, if you cannot directly specify the formula, then you can do some reduction. So for example, you can assume that let's use P0 equals xy, right? And then we can use P1 equals to AB. But this is just for explaining the thought process, right? So we can assume without loss of generality, right? So x is less than or equal to a, right? So why we can do this? So because if it's not, we can switch P0 and P1 because the visit distance time does not change. Obviously, it's symmetric, right? So this means that P0 is in the left of P1, right? So then we have some points. Let's see here, and then you have some points. Maybe let's see here. This is the P1, right? assume that they have the same y coordinates, or you can have some points say here, or you can have some points here, right? So if they have the same y coordinates, for sure you just need to compute the difference of the x coordinate. But if they are here, right, so you can think of first make p naught have the same x coordinate or y coordinate with p1. For example, if you have such a scenario, right, you can first make p1, so x difference, this is the y difference, right? So y difference is larger, so you can first make it same x by travel diagonally and then vertically, right? Or if you see symmetrically, you have y below, so you can also first travel to make them have the same y coordinate, and then you not same x coordinate, then you do vertically downwards, right? So in other words, this problem can be reduced to the problem of same one coordinate are the same, and then compute the difference. So the result actually is the following. So we just need to return the max of p naught, so ABS, absolute value, p naught 0 minus p1 0. So this is the x coordinate difference, and also the p naught 1 minus p1 1. So this will be the y coordinate difference, right? So now once you realize this point, so I guess, so for getting the result, this is super easy, right? So you get the result equals 0, and then you iterate, for example, for I in range, so one length of points, right? So you do say p naught p1, let's see, to be points I minus 1. So here we can write I minus 1 because I is greater than or equal to 1. In other words, I minus 1 is always a valid index. Then we have points I, right? Then we just need to apply these 2 points to this function. So in other words, we increment the result by this distance. Oh, this is in the recursive sense, not distance, but we can use this name, right? So p naught, p1, and then you return the result. So this is a solution to this problem. Let's first do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So again, for as I mentioned at the very beginning, so the problem itself is rather simple. And the important point to take away is that we need to know how to make problem reduction. So this, for example, for this problem, so we just need, this problem is reduced to the problem that we want to find the visit distance for any given 2 points. So that's the one. Another point is that we need to be able to do to think or abstract the problem. So here, you know, if you just think in generally, it might be harder to get this conclusion. But if you do some reduction or think in an abstract way, you can assume x is less than or equal to a, and then you consider 3 cases. So p1 have the same x coordinates, and the p1 much larger. So you can also think if p1, the x coordinate difference is smaller than the y coordinate difference, you can first travel diagonally to make them have the same y coordinate. Then you travel horizontally, right? And then you can think p1 is very large in y coordinates. Then you can first make them have same y coordinate and then travel vertically, right? But these 2 are the same. So then you can easily get this this observation, right? So this is a solution to this problem. But sometimes if you want to have a flavor of object-oriented programming, so you can do something like this. First, here I'm going to change this one to be solution v1, and then I can make this function a class method, right? Because I don't need instantiation. So we can do let's use a class method or static method. So And then what we are going to do, let's see, I'm going to do something like this, cut this part, and then do this. Let's right. So here, what I'm going to do is I'm going to call this class method. So we're going to do solution, not point, not here. So here, solution. Yeah, call this distance class static method. So now let's see. Yeah, it will pass all the cases. Sometimes if you have, for example, this logically maybe this method is subject to this class, you can also use class method. Let's copy this part. So I can comment out this part, and then I can make it a class method. So class method, and then I can use a class keywords. So here, when I call this function, because it's a class method, it's the same call pattern. So let's see, v1. So I changed this one. So now let's test. Yeah, it will pass all the cases. So anyway, for this problem, so we just need to do this version, right? So this is good to know, right? Let's test that. So with that said, basically that's about it for this video. Thank you.